Okay, welcome everybody to this week's Green Bank Community Zoom. Just a few things to talk about before we get to the talk. So we are beginning our track and grout shutdown for the observatory. So the telescope will be out of service for 3 weeks while we work on replacing pieces of worn or cracked track. And we are working on some of the grout pockets beneath the track that supports it, and we're replacing those. So that's kind of normal course of business. We delay this. We can't do this in the summer maintenance period because of the grout is exothermic, and they need cold weather for it to set properly. So that's what we're doing. While we're down, we're aiming to replace to fix the prime focus boom. As those of you who were on the Zoom call a couple of weeks ago, announced that there was an issue with the mechanism that moves that boom. We're talking to the manufacturer about replacement parts. They are due here within a week or so. So we will try to effect those repairs and get the prime focus boom up and running. And we should be back to normal again. So that's good news indeed. Proposals are under review. You should expect to hear in October about the outcome of your Green Bank proposals. And next week we are eagerly anticipating the future of K-band at Green Bank workshop. So that'll be great. And the Gotham team is also having a team meeting here at Green Bank. So lots going on. And it's nice to see some activity and people back on campus. So I'll hand it off to Dave Freyer right now, and Dave can introduce today's speaker.
Hi, welcome everybody. Today we are glad to have Lance Benner, and he's from NASA-JPL, and he'll be talking about radar observations. If you have questions, the talk will be of order 15-20 minutes. If you have questions, please fill them in the Q&A at the bottom of your Zoom window. So go ahead and take it away, Lance.
All right, thank you very much, and thank you for the opportunity to speak. We really appreciate it. We've been utilizing Green Bank for bistatic radar observations of near-Earth asteroids for several years now. This particular talk is going to primarily highlight recent Goldstone and Green Bank radar observations of near-Earth asteroid Apophis from last year in 2021. So this work is actually led by Marina Brozovic, who's the first author on the presentation, but she wasn't available today, so I'm stepping in to pinch hit for her. And it's a collaboration of a number of other people, and in fact, unfortunately, my apologies, I left some people off the list, including Amber Bonzo from Green Bank. My apologies, Amber. So before we dig into Apophis, though, I want to, sorry, I'm having a little, okay, let me get rid of that, a little JPL thing that popped up. I want to point out that there is another near-Earth asteroid event that is coming up very soon that I think you will find very interesting. And this is the Double Asteroid Redirection Test, or DART mission, a NASA mission built by the Applied Physics Laboratory at Johns Hopkins, that is going to slam into the moon of the Didymos-Dimorphos binary asteroid system on September 26th at 2314 UT. So that's early in the evening, September 26th, East Coast time, or kind of mid-afternoon here on the West Coast. This is a mission that it's a planetary defense demonstration test, primarily an engineering test, although there'll be a lot of science that also comes out of it. And this is going to be in the news in a very big way very soon. You probably have already heard some things about it. We are planning radar observations of this beginning on September 27th, about 11 hours after the impact happens. And some of those observations will be bistatic, where we transmit with the 70-meter DSS-14 antenna at Goldstone and receive the radar echoes at the Green Bank telescope. The schedule itself is actually a bit fluid. There's some, so we'll be in touch with folks at Green Bank about this, but there may be some changes because of the delay in the Artemis SLS mission launch. So we'll be in touch about that. But anyway, I just want to let people know this is coming, and it's going to be a very big deal. This is happening in like less than 2 weeks. Okay, getting back to Apophis. So near-Earth asteroid Apophis was discovered in 2004, and it had the rather notorious distinction of having a non-zero impact probability shortly after it was discovered. So it was discovered in late 2004, and the impact probability based on very early observations with ground-based optical telescopes suggested an impact probability of about 2.7% in April of 2029. Additional observations prior to the discovery were then located. The impact probability in 2029 vanished, but there were still possibilities of impact later. We observed this object with radar at Arecibo in January of 2005, and then that summer, and then in 2006. And those observations significantly improved our understanding of its orbit and showed that the close approach that it will make in 2029, which is shown in this illustration here, is going to be only about 5 Earth radii above Earth's surface, or about 6 Earth radii from the Earth's center. That's within the Roche zone of Earth. And as such, it's really unprecedented. This is an object that's in the realm of 400 meters in length on its long axis. And that really close encounter in 2029, on Friday the 13th of April, 2029, is very likely to change the way the asteroid spins. There's even a possibility that it could cause local landslides on the surface and change its appearance, which could potentially have visible effects through spectroscopy. So this is also now the target of a NASA mission. NASA's OSIRIS-REx mission, a sample return mission that will bring back samples to Earth next year, will be renamed as OSIRIS-APEX. It's a long acronym, and I'm not going to try to spell it all out. But that mission, after it drops off its samples from asteroid Bennu with Earth next year, will then redirect and encounter Apophis a number of weeks after this flyby in April of 2029, rendezvous with it and stay with it and study it extensively, including touching down on the surface to try to understand the surface porosity and other surface parameters. So Apophis is a very big deal. It's a big deal for planetary defense. There are many other future close encounters, and there were others where there was a chance of it hitting us. And it's now the target of a very, a major NASA spacecraft mission in 2029. So there's intense interest scientifically and also from a planetary defense perspective. This encounter in 2029 will be close enough that this object will reach third magnitude. And so you could see it if you, for example, were in Northwest Africa, parts of Western Europe, possibly in Eastern Brazil, Venezuela, places like that, for perhaps a few hours. So a little bit more about the asteroid itself. It has been studied extensively by a number of observing teams. Here are some estimates of its effective diameter, and that's the diameter of a sphere with the same volume as the shape of the object. The one highlighted here in red is the one that our team, led by Marina Brozovic, reported in a paper recently. The estimates, vary. Some of them aren't entirely consistent within their uncertainties, but broadly, many of them are clustering in the realm of 350, 340, 380 times meters, that sort of size range. This is an object that rotates very slowly. It's in a non-principal axis spin state, specifically in short axis mode. So the short axis mode of an NPA rotator, it's a little complicated to explain this, but basically it appears to look like a regular rotator, but there's an oscillation about one axis with a slow period of about 11 days. So the fundamental period that is observed by many light curves is about 30.6 hours, but then there's this slower, long 11-day oscillation that is also superimposed on it. So more broadly speaking, there are components of rotation about each of its 3 major axes. This turns out to be quite important, and we'll get to that in a little bit. So it's for those of you who are familiar with asteroid spectroscopy, this is an S-class object. That basically means that it has a composition very similar to that of the ordinary chondrite meteorites, which are among the most common type of meteorites that are observed here on Earth. It has a relatively bright optical albedo. That albedo comes from the diameter from the radar observation, 0.35. That's quite bright. It's elongated. This is inferred from both variations in its Doppler broadening from radar observations and also from light curve amplitudes. And the long axis is about 450 meters. This object has been observed with radar previously, as I briefly mentioned. Here are the dates when we've observed it. The first three apparitions in 2005 and 06 occurred at considerable distances, and we were able to estimate only very basic disk integrated properties and to refine its orbit. They were insufficient to obtain, radar images. In 2012 and 2013, it got closer and was observed first with Goldstone and then with Arecibo, and we did get a series of images. Now, they're not very detailed. The asteroid wasn't close enough for highly detailed images, but they were sufficient to start to understand more of its physical properties, especially its shape and its elongation and size. And I'll be showing you some of those results momentarily. Really detailed delayed Doppler imaging has been possible for many near-Earth asteroids, but not yet for Apophis. It just hasn't gotten close enough. In 2029, it will get close enough. So here's a collage of images from Marina Brozovich's paper from a few years back. These are delayed Doppler or range Doppler radar images. In each image, the distance from the Earth increases from top to bottom, and then Doppler frequency increases to the right. That means that rotation is counterclockwise. In these images, the vertical dimension, as I say, is distance, about 19 meters per pixel. The horizontal dimension is Doppler frequency. In this case, 1/10 of a hertz. The arrows are highlighting possible features. Now these are, as you can tell, these are not very high signal to noise ratio images, but they are sufficient to show some broad characteristics of the object, including constraints on its axis, its long axis. There are hints of some features. For example, this image here in the middle row is showing a collection of radar dark pixels that probably indicate some kind of concavity, or perhaps less likely an area that's simply less reflective to the radar. In fact, we see some other radar dark areas, or at least hints of them on some of the other days. So in each one of these panels, the data is given, and the number of transmit-receive cycles or runs are also given. So the images here, although not at very high signal to noise, are still sufficient to give a sense that this is an elongated object. It appears to have a bilobed appearance, at least a certain aspect, certain orientations. Moreover, the slow rotation that we infer from this, the elongation, and so forth, are also consistent with inferences from light curves, inversion of light curves reported by Petr Pravec at Ondřejov University in the Czech Republic. So here are two animations. On the left is a 3D model estimated from inversion of light curves. And these are using the full spin state, the non-principal axis full state. It's a little subtle, and so a future slide is going to show you more details. Over here on the right is the model that Marina Brozovich estimated using radar data and also utilizing the spin state from Pravec et al.'s inversion of light curves. It turns out that the radar observations were entirely consistent with the spin state estimated from light curves, and did not, in fact, really, in this case, improve on them because the light curves cover a longer interval of time than the radar observations. If you look at this in a bit more detail, so here we have the three principal, let me slow this down for a sec. So the three principal axes are shown in green, red, and dark blue, and the angular momentum vector is shown in a cyan arrow here. And if you look carefully, especially at the blue axis, you can see how it's rolling. So at some level, this looks kind of like a regular principal axis rotator, but there isn't a longer term oscillation that is also evident, that has a period of about 11 days. So you can see the blue axis there is now well away from the angular momentum, then it was close, and now it's moving away as the object is rotating. So this is, again, a non-principal axis rotator. We've seen this with some other objects. Mostly it's in a different mode. It would be typically it's long axis mode, not short axis here. And a long axis mode is similar to throwing an American football and then messing it up, and it wobbles as it rotates. So this is how Apophis is rotating. And prior to recently, this was the most detailed 3D model we've had. So last year, Apophis approached within 0.113 astronomical units on March 6th. That's about 44 times the distance between the Earth and the Moon. And this was the last encounter that Apophis made with Earth at distances close enough for detailed radar observations prior to the asteroid's encounter with Earth in 2029. And at the time this happened, there was still a small chance of an impact with Earth in 2068. And there was already intense interest as a possible spacecraft mission target. And so there was a concerted effort by numerous observers around the world to try to study the asteroid as well as possible. And it was also the subject of a NASA planetary defense exercise led by Vishnu Reddy from the University of Arizona. And a paper describing that was actually published just recently in the journal Icarus. So we observed it monostatically at Goldstone and also bistatically transmitting at Goldstone, receiving at Green Bank. Again, this was work led by Marina Brozovic. So we observed it over the course of a number of days in the first 2 weeks of March. So the broad goals were to improve our understanding of its orbit, to reduce the uncertainties, extend the interval of reliable orbit estimation, try to detect a phenomenon known as the Yarkovsky effect. That's a non-gravitational perturbation on the asteroid's motion, and it's related to absorption of sunlight and then re-emission of heat as the asteroid rotates, and it produces a very gentle push or nudge on the asteroid's motion. There's a related effect that can also change the spin. And this turns out to be quite important for a number of reasons, in addition to affecting its motion and our ability to compute the future motion with the implications for impact hazards. It also is dependent on the density of the object. So if you can observe this subtle effect, it provides a way to constrain the density. And if you have a shape model, so you know the volume, also the mass of the object, which, you know, the density, of course, can help you understand the internal structure and its formation. And possibly also the thermal inertia. We also hope to improve the shape and other, and improve our ability to predict the orientation of the asteroid in 2029. And that's important because we expect Earth tides, to change the spin. All of this is very important for missions. And at the time we did the observations at Goldstone and Green Bank in 2021, we didn't know that this was going to be an asteroid mission target. The selection of the OSIRIS-REx mission to fly by Apophis happened after we observed it. So now the observations are even more important than they were at the time that we conducted them. So the signal to noise ratios were not very strong. They were even weaker than they had been, or comparable to what they were in 2012, 2013. But here's a series of bistatic Goldstone Green Bank images, a collection from 3 days in March of last year. Here in the lower left are some echo power spectra. In this case, one polarization, shown on a number of different dates. Although the signal to noise ratios are weak, they do indicate, very strongly imply again, that this is an elongated object. There are hints of a central dip in its shape. The elongation is again consistent with this rotation period. And importantly, we obtained new measurements of the asteroid's distance that completely eliminated any chance of an impact in 2068. That impact probability was quite small, but now it's basically zero. So Marina has done some preliminary modeling on this and has updated the estimates of the spin state. It turns out that the observations from 2012 and earlier to estimate the spin state needed an update. If you just took those observations and blindly propagated things forward, you would obtain, for example, an orientation like this on one day, whereas that didn't provide a very good match to some of the data. Here's one example of a single spectrum. And she updated the spin state at the same epoch, same moment, and you can see that it looks quite different. And so this, it turns out, was necessary to improve our understanding of both the spin state and the shape. And this is also consistent with the preliminary light curve results from last year. Here's another example, in this case, the delayed Doppler image. Again, the images have weak signal to noise. They're over here on the left. And here is a fit, and here is the plane of sky orientation of the shape with the spin axes and the angular momentum vector. This is the shape that was used to compute this fit, and then we would compare that with the data. And you can see that if we use the old spin state from 2011, 2012, 2013, it does not really match the data very well. Now, this is not a perfect match yet, and we will revise this when the the updated spin state from the light curves from last year is available. That's still in preparation by Pedro Province. This is a much more detailed view of what I just said. I won't try to trouble you with all this, but the old spin state, if we propagated that to 2018, means that's the date it was published. If we propagated that to last year, then this is what we obtain. And the new spin state shown for the fits to the data from 2013 and fits to the data from last year are shown over here on the right. And the fits have definitely improved. And the new spin state fits the old data and the new data, whereas the old spin state didn't. So some of this I've already said, so there's more of this coming, and more work coming on this. A more detailed paper based on the radar data will come out as soon as the spin state is available from the light curve, because they cover a much longer interval and will provide more precise estimates of the spin state than we can obtain with the radar data alone. And all of this is going into planning for the OSIRIS Apex mission in 2029. So I think my talk is getting a little bit tight. So let me briefly say that Apophis will be an extraordinarily strong radar target in 2029. We plan extensive observations. Goldstone can image up to 2-meter resolution. Haystack's Hoosier facility could in principle obtain resolutions as fine as 20 centimeters. We're hopeful that Green Bank will have an actual radar capability, not just receiving but transmitting by then. We'll see how that goes. Hope it happens. We expect to obtain images with detail comparable to or better than this image here of a different asteroid. And there will be a lot of things that we hope to do. We should see extraordinarily fine levels of detail on the asteroid in 2029. Should be able to do detailed interior sounding at longer wavelengths, see changes in the spin state, estimate the moment of inertia ratios before and after the encounter, which can help us understand the internal structure, mass distribution within the asteroid. This slide also talks a little bit more about some of those things that we can do, more speckle observations, radar polarimetry, detailed radar ranging, and so forth. And I think with that, my time is up, and so I'll stop there and see if there are any questions.
Thank you, Lance, for a very interesting talk. It was great to see this background information. I learned some stuff about the NASA missions. We do have a few questions that come in. I'll read them out to you, and then you can answer them. And feel free to use the Q&A window to ask questions. One of the questions, I'll just say, it was asking about, will your talk be posted? And I provided a link in the Q&A. Yeah, we post all of our Zoom talks on the GBO web pages. We had a comment about the source being about the size of Arecibo. But anyway, the first real question that came in is, what is the likelihood of Apophis being another of the rubble pile-like asteroids, or is its size and gravitational profile such that it indicates that it's more of a solid object?
Well, the probability that it's a rubble pile, we think, is actually quite high. The evidence from observations of hundreds of near-Earth asteroids obtained to date, especially of their rotation periods, their spin, is that many of them are rubble pile objects. That is, for those of you not familiar with this, these are like collections of blocks that are very loosely held together by the gravity, and perhaps very weakly held by other things like van der Waals forces and stuff, so forth, things like that. There aren't very many Earth-approaching asteroids that are known to be monolithic, competent, solid objects. There have been also, of course, spacecraft results very recently. For example, NASA's OSIRIS-REx mission that went to the asteroid Bennu, that clearly demonstrated that object, which is somewhat larger than Apophis and rotates much more rapidly, is basically a rubble pile with a very high porosity. The Hayabusa 2 mission from Japan went to an asteroid Ryugu that is also very, very porous. And there are other examples of small objects. The original Hayabusa mission encountered Itokawa, that also is a very porous object. There are numerous lines of evidence. So it seems that the vast majority of near-Earth objects are very likely to be rubble piles. It's actually, from what we can tell, anomalous to find one that isn't.
Okay, thank you. the next question, or as a statement, the GBT Ka band radar with enough power, and just for background, we're planning on doing Ku, I believe, and not Ka. But anyway, would be a nice addition to what we know about Apophis. It seems to me, the person says, and I'm sure you've thought about it. Do you want to say anything about the potential use of the GBT in studying this source, or in general for radar?
Yeah. I mean, that would be fabulous. I mean, the Ka band, of course, is a higher frequency than we used. I mean, our observations, I didn't talk about this, but our observations were at X band, at 3.5 centimeters. Ka band is going to be at a significantly higher frequency. And so that'll provide finer frequency resolution, or that's the horizontal direction in the images that I showed. And given that this is a slow rotator, that'll be quite useful. It'll show quite a bit more detail than we were able to see at X band. So we would be delighted if that happens.
Okay. Is the spin state unique? Doing that for Bennu was a challenge with just a few epochs of observations, but there's a lot more data for Apophis.
Yeah, thanks, Mike, for that question. In terms of uniqueness, if Marina is on here, she's probably better qualified to directly address that. I mean, sure, you can probably find my expectation is, given that there are, of course, uncertainties in the estimate of the spin state, that you can find them some subtly different spins that are going to provide comparably good matches to the data. But so in that sense, probably not. But just how small those uncertainties are likely to be when the light curve inversion is fully complete, and then the light curve plus radar inversion is complete, I'm actually not really sure. So Marina, if you're on here, please feel free to put something in the chat, or so that we can look at that in more detail.
Okay, another question. Could you remind us where the asteroid would be visible from as a third magnitude object? You mentioned.
Yeah, sure. So the close approach is the closest approach when the asteroid will be brightest will happen during the nighttime part. That is when it will be night in parts of Western Europe and parts of Eastern South America. And of course, also Western Africa. So for example, Morocco would be a good place, because it tends to have very, a lot of clear nights there, or other parts of even Saharan Africa, the western part of it. Western Europe, like southern Spain, France, Portugal, the Canary Islands, the Azores. Those would be really good places. Possibly Eastern Brazil. I mean, quite likely, although in terms of the likelihood of clear skies might be quite a bit less there. Venezuela, other countries in Northern South America, possibly in some of the West Indies. So, I mean, I haven't actually checked the circumstances regarding visibility in Eastern North America, but here on the West Coast, the best time to see Apophis when it's relatively bright will actually be the night before the closest approach, when the asteroid will reach 7th magnitude. And so if you know where to look, you should be able to pick it out in binoculars pretty easily. But from the West Coast, it won't be bright enough to see naked eye. I would imagine the East Coast is likely to be similar, but maybe even a little bit fainter.
Okay, thank you.
I don't know precisely. Okay.
Okay. The question we have a question about DART. But will the DART radar observations place any constraints on the ejecta cloud?
Okay, yeah. So this is about the DART spacecraft impact with asteroid Didymos on September 26th. And so one of the questions is, will there be a big cloud of dust or other debris? And if so, could that be detected with radar? Could it be detected with optical telescopes or others? At the very least, they should be able to place some kind of upper bound if we fail to detect anything. But we don't know. This hasn't been done before. Slamming an asteroid, a small spacecraft into an asteroid, a rocky asteroid, has not been done before, and so we'll find out. I mean, that's why one of the reasons why the observations we're doing only 11 hours after impact are so important, is because that's like the shortest time interval between the impact and when we can observe. And so if there's a cloud of material, that might provide our best chance to see it. To provide a little bit of context, there of course have been radar observations of comets dating back, decades at this point, and they have detected the tails and the coma from, well, primarily coma, not really the tails as much, from the comets, some comets, as well as detecting the nucleus. And so it's conceivable that that the detection of Dimorphos with radar might also include something that looks somewhat like a comet coma, but we don't know. Now we'll find out, I hope, on September 27th.
Okay. I think you mentioned the upcoming Didymos observations may be affected by Artemis. Is this because Goldstone is needed for communication?
Yeah, so Artemis is of course the big rocket that is it will take astronauts back to the moon in a few years. And so there's a test launch that they had hoped would launch on Labor Day weekend, but has now been postponed. And the current date that I've heard was September 23rd or 27th. And the reason that could affect what we're doing with Goldstone radar observations of Didymos and its moon Dimorphos is because the Deep Space Network is needed to track the Artemis spacecraft once it gets beyond a certain distance from the Earth. And so obviously the Artemis spacecraft is a very high priority within NASA. And so the schedule will be shuffled. And so missions to other planets, for example, may have to reschedule, and our radar observations may have to reschedule. I haven't seen the detailed plan yet for that. There's a contingency plan already in effect, but I haven't seen any details. It's likely we'll find out about that pretty soon. So yeah, it's because the antennas are going to be needed for communications. Now, in terms of NASA tracking the DART spacecraft as it approaches and then hits Dimorphos, that's not going to change. I couldn't imagine they would do that because that's a critical event. And the tracking for that is actually going to happen with Deep Space Network antennas in Australia, and with backup with the ESA facility near Perth.
Okay, thank you. There are a couple of notes in the background here about the GBT. We're planning KU band, not KA band for our radar system. So 15 gigahertz instead of whatever 30 gigahertz. The next question though, are there any planned JWST observations?
So I'm guessing that this is a question about Didymos and not Apophis. And the answer is yes. Yeah, they are. They're going to be telescopes all over the world looking at Didymos and its moon Dimorphos. There will, of course, be extensive light curve observations to try to measure how the orbital period changes. It's expected to accelerate. So the orbital period of Dimorphos around Didymos is supposed to shrink. It's supposed to be faster. Oh, okay, yeah, Mike Nolan chimed in about JWST. But that's later on.
Okay, he said it was moving too fast.
Yeah, that's in 2029. Okay.
Any chance for outgassing during the close approach?
So for Apophis, assuming this is about Apophis, that's an interesting question. I hadn't heard about that. I mean, it's not thought to be a cometary type of object, but given how close it's going to approach, it's conceivable that there could be things that we could observe due to its extraordinary proximity that have not been observable by previous asteroids. Let me give you an example. When the OSIRIS-REx mission rendezvoused with Bennu, one of the startling discoveries was that there were small particles apparently being wafted or ejected off the surface, and nobody expected that. And we had not seen that from the ground. Now, that isn't necessarily a consequence of its close approach to Earth, but in a sense, the Apophis flyby with Earth in 2029 will be like a spacecraft encounter with the asteroid because the distance is so close. And so it's conceivable that there may be things we might see. I mean, there are recent predictions that there may be some particles and fields effects that hadn't really been contemplated, in addition to the more obvious things like changing how the asteroid spins, and possible small landslides and rock slides and things like that.
Okay, the next one, on the coordination of the Apophis campaigns, Any hints / developments post the latest Apophis workshop? So that's more an insider question, I guess.
Well, I just mentioned one about possible effects in particles and fields. That's come out quite recently, a realization that there might be something there to observe. So that's not my area of expertise, and I know people are working on papers that describe that, but I really don't know very much about that. I mean, it's going to penetrate well within the Van Allen radiation belts, and so yeah, I suppose it's possible that there might be some lofting of particles from that. I'm kind of making an educated guess here. So again, if there's somebody who knows more about this than I do, who's on the presentation, feel free to chime in with comments.
Yeah,
I mean,
if we want to have a discussion, I mean, we can unmute you so you can speak. Just raise your hand. Go ahead.
I mean, one of the other earlier speculations about the Apophis encounter in 2029 was that if the asteroid does in fact have a rubble pile shape, which we expect, one of the things people were wondering is whether the whole shape might change a little bit. And there's been extensive theoretical work done by a number of different research teams on that topic, and it's no longer thought that's very likely. It's not completely impossible, but I think that would be a major surprise.
Okay, a question. Will monostatic observations of Apophis from any radar be possible? If not, in the Goldstone GBT bistatic observations, assuming the GBT radar's transmitter is operation, how will transmitting frequency X versus KU and be prioritized?
Okay, so yeah, so thanks for the question, Dylan. It's try to go through this quickly. The Apophis, of course, will be visible at a considerable distance for weeks prior to the actual moment of closest approach. And so monostatic observations from Goldstone will certainly be possible for a number of weeks, I mean, including very detailed delayed Doppler imaging as the asteroid gets close and after it moves away from us. The asteroid will become a daytime object for visual observers, optical observers after the closest approach. But with radar, we'll be able to keep tracking it for weeks afterward. Now, when it's within a couple of days of closest approach, then bistatic observations will be preferred because the round trip light travel time will be very short. It could still be observed, for example, with the Haystack 37-meter antenna in Massachusetts, the Hoosier facility, which can operate at both X and W band. And they could obtain very, very detailed images. Those are the ones I mentioned earlier that could be as fine as 20 centimeters or perhaps even finer in resolution. The ISCAT facilities in Norway could do it, both the existing 32-meter antenna and the upcoming ISCAT array, although they wouldn't be able to get detailed Doppler resolution by virtue of their transmit frequencies. There could also, in terms of other monostatic observations, those would be the principal facilities that at closest approach that would be utilized. I suppose we could do pulsed observations of Goldstone, but those actually we can't do that bistatically. They'd have to be monostatic. So the bistatic observing is going to be the preferred mode when the asteroid is within a certain distance of the Earth. And it could involve transmissions from the 70-meter telescope at Goldstone, reception at Green Bank, or reception at one of the 34-meter telescopes at Goldstone, transmissions from a 34-meter telescope at Goldstone and reception at Green Bank or somewhere else, or the VLBA. We also do observations with we being the general community, not just us. At Canberra, this is work led by Shinji Horiyuchi with the DSN facility down there. We would love it if Green Bank has a radar transmitting capability by 2029. That would be really, really useful. I mean, Haystack could transmit and we could receive with Green Bank. That capability is pretty much there right now. So there are numerous options at the closest approach. Bistatic is probably not the way to go, however.
Okay.
Regarding prioritization, we'll deal with that later. It's too early to worry about it.
That is so true. 7 years out. Did NASA's previous deep impact mission to Temple 1 provide any orbital change data?
My understanding about this is that the nudge that the spacecraft imparted when it slammed into the Temple 1 comet nucleus was too small to detect. That comet is a lot larger than Dimorphos. So Dimorphos which is the small moon that revolves around Didymos, is only about 150, 160 meters long. The comet nucleus is well over an order of magnitude large. I think it's in the realm of 7 kilometers. I'm going by memory here, so it might be off, but it's very, very different sort of gravity regime. And I don't think there was any expectation they would see a nudge, and I don't think they observed one. And it would also be, of course, very difficult to pull that out relative to the natural non-gravitational perturbations that result from outgassing from the nucleus itself. That can be a very powerful effect on comets. So anyway, I hope that that answers the question.
Okay, and I think we made it through all the questions. Thank you, Lance, for your excellent talk. I think you might get an award for the largest number of questions coming in.
Oh,
So it shows the interest in the field, and we thank all the participants for joining. Our next community Zoom will be September 28th, where Jane Greaves from Cardiff will be talking about GBT photometry, seeking pebbles and protoplanetary disks. So thank you again, Lance, and thank everybody for joining. Till next time, I will go ahead and sign off the Zoom. Bye.
All right, thank you.